As we continue our study of subatomic particles and the structure of an atom, we've previously learned how to model an atom in the terms of drawing a Bohr diagram, which allowed us to annotate the nucleus in terms of the number of protons and neutrons that reside inside of it, and to plot the electrons on the different energy levels, and then determining the number of valence electrons by looking at the number of electrons in the outermost ring. Today, we're going to learn how to model Lewis dot diagrams, which is a significantly easier way to model an atom. But what is a Lewis dot diagram? A Lewis dot diagram is a model that shows just the element symbol and the number of valence electrons. And in order to gain an advanced understanding of this concept, we're going to do a multitude of examples together, and then you'll do a multitude of examples on your own. If you don't currently have a periodic table in front of you, please pause the video and retrieve one now. After you've retrieved one, then you can press play and keep going. Our first element that we're going to do together is aluminum. And in terms of drawing a Lewis dot diagram, I don't really need to care about the mass number because I'm not concerned about the nucleus, I'm just concerned about the number of electrons, which we are currently assuming that all these atoms are neutral, which means that the number of negative electrons is going to be equal to the number of positive protons. So after looking at my periodic table, I determined that the atomic number for aluminum is equal to 13. So because my atomic number is 13, that means I have 13 protons and 13 electrons. So if I were to draw a Bohr diagram, I'm just going to draw a little dot for my nucleus. And in my first level, I can hold a maximum of 2 electrons. But I have 13, so I'm going to have to draw another level. And in my second level, I can hold a maximum of 8, so that gives me 10 total right now. But I have 13, so if I have 10 drawn, but 13 total, that means I have 3 more to go. And so in my last level, I would have 3 valence electrons. So because this is the number of electrons in my outermost level, that means I have 3 valence electrons. So when you draw a Lewis dot diagram, you first write out the element symbol. And the only thing that you're drawing are dots to represent the number of valence electrons, and there's a specific order that we go in. We start at the top, and we have 1 dot on the top, we go to the side, and then the bottom. So because I have 3 valence electrons, I have 3 dots. The next example we're going to do is sodium. And sodium has an element symbol of Na, and after looking for it on my periodic table, I find that it has an atomic number of 11. So because its atomic number is 11, that means I have 11 protons. And because the atom is neutral, that means I have 11 electrons. So now I'm going to draw my Bohr diagram. And my nucleus is going to be represented by a dot. And in the first level, I have 2 electrons. So if I have 2 down and I have 11 total, that means I have 9 more to go. And the second level, I can have a maximum of 8, and I'm going to fill that up because this is now a total of 10 electrons drawn, but I have 11 total, so I have to draw 1 more ring. It's a really good circle. And so I have 1 electron left, so this represents my 1 valence electron. So to draw my Lewis dot structure, I'm going to write the element symbol of Na, and don't forget guys, capitalization counts, so big N, little a. And I only have 1 valence electron, so I'm going to draw 1 dot on top. As you can see, doing the Lewis dot diagrams for even just these 2 elements is significantly easier than drawing the Bohr diagrams and all the levels that it needs. We're going to do 3 more examples together before I let you off on your own, and it's important that you watch the next 3 so you understand that there is a certain pattern and process we take in drawing these Lewis dot diagrams. Our next example is chlorine, and after looking for it on my periodic table, I see that I have an atomic number of 17. So because my atomic number is 17, it means I have 17 protons, and because it's a neutral atom, it means I have 17 electrons. So now I'm going to draw my Bohr diagram, and I notice that chlorine is in the 3rd row of the periodic table, so I can rightfully assume that there are 3 energy levels being used for this element. So in my first level, I know that I can hold a maximum of 2 electrons. In my second level, I can hold a maximum of 8. So by filling up the first 2 levels, I've taken care of 10 out of the 17 that I need, which means that the last 7 are going to go on the last energy level. So this means that I have 7 valence electrons. So for chlorine, it's going to be really tempting to do 2 at a time, but you should not do that because we need to follow the pattern, and this is important for bonding. So when I have 7 valence electrons for chlorine, I have to think about it like chlorine's in a box. So I'm going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. The next example is going to be fairly simple. It's hydrogen, and hydrogen's atomic number is 1 after looking for it on my periodic table. So because the atomic number is 1, that means I have 1 proton, and because the atom is neutral, I have 1 electron. Because hydrogen is the first element and it's in the 1st row of the periodic table, I can assume that I only need 1 energy level. And because hydrogen has only 1 electron, it means I only have 1 electron on my energy level, and then I'm done. So, but its Lewis dot diagram is going to be its symbol with 1 dot. Now, something I want you to notice is that Na and H, or sodium and hydrogen, have similar Lewis dot diagrams, and that they only have 1 dot each. Now look at your periodic table. What do these 2 elements have in common in terms of their placement? You might notice that Na and H are in the same column. And this is important for the next part of our lesson today. But the last example we'll do together is with carbon. And carbon's atomic number is 6. So because its atomic number is 6, that means I have 6 positive protons. And because the atom is neutral, it means I have 6 negative electrons. Looking at which row carbon is in, I see that it's in the 2nd row, which means I'm going to have 1, 2 energy levels. In the first ring, I can hold a maximum of 2, so that takes care of 2 out of my 6. But I only have 4 left, so I can put just the 4 in my 2nd energy level, which means I have 4 valence electrons. So my Lewis dot diagram is going to be carbon, and this is why following the pattern is important. Because we're going to have 1, 2, 3, 4 dots total representing the 4 valence electrons, but it's important to note that the single electrons are going to represent slots in which that atom can bond with other elements. So we'll learn in our bonding unit that a pair of electrons is not eligible to bond with another atom, but a single electron is. So that's why following the pattern is important. Now pause the video and attempt the independent practice on your own, and you will not receive full credit until that's complete. Once you're done with the independent practice, press play and move on with the rest of the lesson. Now, drawing Bohr diagrams and converting them to Lewis dot diagrams is still a significant amount of work, but all of this is leading up to kind of the cheat or the hack of the periodic table, because we can determine the number of valence electrons based on the group number on the periodic table. Group numbers are actually very simple to denote. We're literally going to count left to right 1 through 18. So this first column is group 1, the second column is group 2, the third column is group 3, and so on. And this is an interactive periodic table, which makes it a little harder to write on. But I'm sure you understand the idea behind it. So going back to the guided practice from the front, you saw that NA and H are in the same column. So NA and H are in the same column, and they both had just one dot. And they're in the first column. So because these two elements have one dot each, that means they have one valence electron, and because they're in the same column or family, we can assume that every element in group 1, that whole column, has one valence electron. Which means that every atom in group 2, in this blue column right here, has 2 valence electrons. And we're going to skip what we call the transition metals, and I'll explain why in just a second. We're going to go to group 13, and everyone in group 13 has 3 valence electrons. So if we look at our representative with 3 valence electrons, that's aluminum, and we see that aluminum is right here in group 13. Carbon in group 14, we diagrammed as having 1, 2, 3, 4 valence electrons. So based on the pattern, we can assume that every element in group 14 has 4 valence electrons. Following the pattern again, we can assume that group 15 has 5 valence electrons. Group 16 has 6. Group 17, which we had a representative from before, in chlorine. Chlorine is 1, 2, 3, 4, 5, 6, 7 valence electrons, and it's in group 17. So group 17, every element has 7 valence electrons. And then in group 18, every element has 8, except for helium, because there's always an exception in chemistry. There's always some gray area. And we'll go over noble gases when we start talking about families of the periodic table. So you might be thinking that's really neat and really nifty, but why do we skip the transition metals, which is this group right here? And the reason we skip the transition metals is that transition metals have a varying number of electrons. And varying is another word for changing. So they don't fulfill the pattern very nicely, but there is a way to determine its charge for bonding, but we won't need to worry about that until our chemical bonding unit. So knowing that this is our pattern, our lives are about to become a lot simpler in terms of drawing Lewis dot diagrams. So as a reminder, everyone in group 1 has 1 valence electron. Everyone in group 2 has 2 valence electrons. So it's kind of like 1, 2, skip a few. And then group 13 has 3 valence electrons. Group 4 has 4 valence electrons. Group 15 has 5. Group 16 has 6. Group 17 has 7. And then this part of group 18 has 8 valence electrons, while helium only has 2. And again, that's something we'll cover more when we talk about families of the periodic table. So now let's go through some examples of how to use this pattern effectively. And our first example is sulfur. So what I'm going to do is I'm going to look for the group number first for sulfur, which means I have to look for its element symbol. And I'm going through the rows and I find it right here. So before we were looking at rows to determine the number of rings to use, but now we're going to look at columns. Be like, oh, well, it's in group 16, so it's going to have 6 valence electrons. So group 16 has 6 valence electrons, and it actually also has an atomic number of 16. And just to make your teacher happy, we're just going to review that. If it has an atomic number of 16, it means it has 16 protons and 16 electrons, because we're still assuming that all atoms are neutral. This will not always be the case. So we're going to write the element symbol, which is a capital S. Because it has 6 valence electrons, we're going to have 1, 2, 3, 4, 5, 6 valence electrons noted. And we have 2 pairs and 2 single electrons. And this is important, again, when we talk about bonding. Looking at fluorine, I'm going to look for the capital F. So I'm going along the rows, not in the first one. Going along the second row. Oh, right there, element number 9. So it has an atomic number of 9. Means it has 9 protons and 9 electrons, but it's also in group 17. So this column is the 17th column going from left to right. So it's in group 17, which means it has 7 valence electrons. So because this is the only number I have to care about in terms of Lewis dot diagrams, I'm going to draw the capital F and then plot my valence electrons around the symbol as follows for 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So fluorine has 3 pairs of electrons and 1 single, which means when we start talking about bonding, it can only bond with 1 other atom. So the last example we're going to do together is for boron. And looking along the periodic table, okay, but I don't see a capital B in the first row, but I see a capital B in the second, in group 13, because it's the 13th column. So 13, its atomic number, because we always like to do a little bit of review in this, is 5, which means there's 5 protons and 5 electrons. But because it's in group 13, I'm going to have 3 valence electrons, because that's what my previous pattern told me. So again, this is the only number I really care about in terms of Lewis dot diagrams. So I'm going to draw a capital B and then draw my 3 valence electrons as 1, 2, 3. And again, because I'm following the pattern, I know that I'm going to have 1, 2, 3 bonding spots and no pairs of electrons. So because I'm pretty sure you have a pretty solid handle on this, I'm going to need you to attempt the last 2 elements on your own. And once those last 2 elements are attempted, that means that you're complete with this particular lesson, and you can move on to ions once you've checked in. Good job, guys.